Hello, welcome to our talk. My name is Cesar Delgado. I'm the manager for the open source team at Siri, and this is DB Spark committer in PMC, and we're going to talk about making nested columns a first-class citizen in SQL. So let's get started. So first of all, Siri probably needs an introduction. I'm sure very few of you have heard her. So Siri is the most popular intelligent assistant that runs on every single part of the platform inside the Apple ecosystem. Hopefully most of you have iPhones, and hopefully every person that has an iPhone either asks for jokes or something about Siri, because that pays for my paycheck. So please make sure you do that as soon as you leave the building. So what does the open source team at Siri do? Sadly, for a while, open source and Apple haven't been something that's been said in the same sentence. It's something that we're trying to change over time. We've made a lot of investment into current open source projects that Siri depends on. My team is actually comprised of Spark Hadoop, HBase PMCs, and committers. And we work on this daily to improve the products at Apple scale so you guys don't have to learn the lessons that we've learned. We basically, inside Apple, we talk open source, we live open source. The work we do, we put it back into the community, and we do everything in public. As you guys see, we're going to talk about some JIRAs. You can go and see what we've been talking about. So we're trying to kind of open up the world of the internal Apple ecosystem, at least in our data platform and how we use it, to everybody else in the community. So let's talk a little bit about Siri data. As you can imagine, Siri is an intelligent assistant. This is Spark AI, so we have to talk about AI and ML because it's in the title. So we're going to talk a little bit about it. So you can imagine there's a lot of training that needs to happen for Siri to do what Siri does. And of course, as most people should know, part of AI is 90% data cleanliness and 10% of the easy thing. I'm in operations, so I think that's easy. But we need to find a way of actually doing it. One thing about Apple is we actually believe privacy is a fundamental right of all our customers. That adds some complexity in the way that we actually do machine learning and do AI for Siri. But we believe it's a valid investment and totally worth doing just to make sure that our customers are safe and their privacy is maintained. So let's talk a little bit about scale. We have a large amount of requests. We have data centers all over the world. If we didn't, we would be silly because the speed of light is finite and we need to get those requests as fast as possible. We also use Hadoop and Yarn, which may or may not be a surprise, but it's the only way to process this kinds of data at the scale we're working on. On HDFS, we currently have hundreds of petabytes. The lawyers won't let me take exactly how much, but it's large. And then, as you can imagine, a lot of data comes in from our production systems that we have to process. Most of that data, as you can imagine, gets cleaned up and worked out by some amazing data engineers that are over here in some places. So thank you very much for keeping our Hadoop cluster smaller, so throwing away part of our data, or else we'd be in big trouble. And then, as you can imagine, we're at SparkCon, so of course, most of our job's in Spark. But just to remind most of you, because I'm an operations guy, sometimes the legacy stuff won't go away. So you still have to remember of your other users and kind of the choices you're making. We have legacy stuff. Hopefully that'll get moved to Spark, but we'll see. So let's talk a little bit about our data, because this becomes the interesting bit and why kind of we got to where we are now. For better or worse, the data that Siri produces is deeply nested. Which is not very normal. But the interesting part about the data is that nested actually holds information on how the data is represented. So we could either flatten it out and lose a whole bunch of interesting bits and bytes, or we can keep it as it is and get some kind of metadata information for free. So when I say deeply nested, what does that mean? We have about 2,000 columns, or fields, if you will, and they're actually only in 5 columns. So when we say deeply nested, we mean it. We're not just saying, oh, we have 2. No, we have an interesting thing. When we tried throwing this into Spark, we had some issues, so it started us down this road. Our data is stored in Parquet. Hopefully most of you are using some sort of columnar format, being ORC, being Parquet. If not, your life will be better when you move over. Just spend the effort and do it. It's totally worth it, trust me. The interesting bit, and it might not be a surprise to most of you, is we have this gigantic data set. Most people don't care about the gigantic data set. They just care about a small subset of what's in there. So it doesn't work. Literally in Spark at this moment, this just doesn't work. So it's a SparkConf presentation, so you need an example, so we're going to give an example. So imagine if you have a real estate application of some sort, and you want to model your data. So the data, of course, will have houses, and then those houses, they're in some sort of school, and they have an address and stuff. And so you have to, describe your data in some sort of case class. Nothing fancy. But when you go in and you actually ask and say, Spark, hey, by the way, can you show me this? You get a nested structure. Anybody surprised? Hopefully not. So let's ask, I live up in Portland. Let's ask for houses that are worth, more than 2 million, so 10 bedrooms, a couple of thousand bathrooms. I heard you can get something similar here in San Francisco for the price-ish. So what happens? You tell Spark, it goes, and it comes back. If you guys take a look at what's in yellow, it comes back with everything, right? We only asked it for houses that are here, address and city, but it came back with everything. You guys are on this side, I get to do this. So we only needed a couple of things, but in the end, we just read the entire thing. So imagine you have our scale of data, and you do this. What happens? Very sad data scientists, because they just can't get their work done. They'll go get coffee, come back, it's like, it's still there. I want to play, Tetris on my phone. That's not really what they do. They actually work really hard. So we actually went in and made a couple of JIRAs to add the nested column support into what we're doing. Parquet is already columnar. Parquet gives us most of this information. We're just not using it. We're not using it. So you can imagine Parquet, like I said, if you guys haven't moved to something columnar, it helps compression and encoding. And it already has all these recursions. So we don't have to do much work on the file system level. Most of the work that we had to do is on Spark. So we literally went ahead and did that, and somebody way smarter than me actually did the work. So I'll hand it over to DB.
Yeah, cool, thank you. So 1 second, okay. So yeah, I want to do a quick survey. How many of you guys are dealing with the nested data structure? Okay, wow, pretty much everyone here. And then do you guys suffer from the performance issue? No? Okay.
Oh, come on.
Okay. So
come on.
I
it's a safe place.
No, I know, because, they make things slower so PM can, ask them to less work. So I'm joking. Anyway, so yeah, so we find out we have a lot of performance issue because, as Shisa mentioned about that, we have 2,000 nested column inside only 5 top columns. So every time, let's say we only need 2 or 3 columns, the entire data has been read. But however, inside Parquet, it's kind of being stored as a flattened data structure. So each nested structure is actually, each nested column is actually stored as a separate column inside Parquet. So in theory, we should be able to just get a subset of the data from Parquet, and we are reading the entire bunch of data. So that's our intuition, and we want to fix the problem and work on that. So in this, in Jira, Spark 2502 and the other one, so people, as a community, we are working on fixing this issue. So let's say, we do the same query, for example. So we just queried it on the data, a city with the house price larger than $2 million, for example. Okay? So with this fix, we are able to just read 2 columns over here. Address, city, and also price inside the facts in the top columns. So we only read 2 columns over here. However, if you look at the execution plan and look at the push filter, so push filter is a filter that will be pushed into the Parquet reader, so Parquet can release data before bring the data back to Spark. So it's a push filter. So you can see that these two, we have a filter condition. We have predicate, which is looking for price larger than $2 million. But this one is not being pushed into the Parquet reader. So how can we do it? So we implement these features in Spark 25556. So the pull request is out, but not merged yet. We are still working on some API changes in Spark to make it merge, but it's already open source, and we are going to try to merge it by Spark 3.0. So with this, we will be able to push the filter, actually. So you can see the push filter gonna have the fact the price larger than $2 million. So in this case, we are able to read less data because Parquet reader can help us to filter out those low group that is not satisfy this condition. And typically when you have a proper design like a data warehouse, you probably sort it by certain columns, for example. So in this scenario, you are able to skip the entire file sometimes. That can help your performance dramatically. So that's the one thing we are doing. And by the way, we are not building this to make the house price query faster, to make the house price more expensive in San Francisco. So just joking. So anyway, so let's say we are looking for another problem. So basically, the problem is that the schema pruning features inside Spark that has been merged. The problem is it's doing the schema pruning just right after the data reading. So if you apply any operations, after you, if you apply some operation after you read the data, you can have read Parquet files, and you do limit or repartition or whatever, and then let a subset of the columns, subset of nested column afterward, okay? So here is an example. Let's say you have a UDF that is only going to use CT, stat, zip code, for example, and then first of all, you read the data and you do repartition, whatever operation, can be sorting or whatever. And then you only select subset of the column. We are looking for only 3 columns. So even with the feature we have right now, we still going to read the entire data structure. And what is the problem over here? Okay, because I saw we already fixed the problem. But the problem is that the schema pruning feature currently merged in Spark. The way it does is that we look at the, after we read the data and we look at the schema you are actually asking for, like a nested structure, and we only we applied it into the Parquet reader to read subset of the data. However, with this case, Spark has to know, how to push down the projection or prune the data after the repartition operator or expression. So we need to talk about how Spark does this work. So there is something called attribute inside Spark. An attribute is the best left named expression inside Spark. And this represents a top column inside Spark, okay? So it's a top column, root columns. And if you want to get a nested data structure inside Spark, how does Spark work? So Spark gonna apply an expression on top of the attribute, and for example, like a get chart field. So basically, you have a get chart field on top of the attribute, and get chart field can say, oh, I want to get column A.B, the second column in the nested chart. And then you get a second columns. However, in the Spark, we have a bunch of pruning logic, column pruning logic, but those stuff are designed to down in the attribute level. So the problem right now becomes inside Spark, there's no easy way. You just get a subset of the nested column, and then carry it along in the execution plan. So you either get the entire root label, or you just get pretty much a really subset of the, you either get the entire root column, or you prune it out entirely. So there's the problem inside Spark, and there's no easy way to fix it. And there's the problem we run into over here, for example. So basically, we either prune the entire root column, or we get the entire thing. And right now, we needed a nested structure. So as a result, we need the entire stuff over here. So, okay, so let's talk about how we can fix it. Okay, so this is the PR done by us as well. We have the foundation to support reading the subset of data from the Spark with Parquet. And then right now we have a problem that we cannot push down the projection through many operator, and that's not really good. So one of the solution we found or we did is that we try to flatten out the nested data structure using alias inside Spark. So for example, after the data you are reading, okay, so you have a really complicated nested data structure, and we only needed 4 or 5 nested data, a nested column from that. So we do a projection right after data reading and create an alias on the nested data structure, so that after that, all the data view will be the flattened view inside Spark. Although it's kind of like a nested data structure, but we create a flattened view after data reading so that we can read subset of the data like in the really early of the execution point. So how does it look like? So let's talk about this and a query. Okay, so we have a query, we select everything from home and do repartition, and we are just looking for 3 columns out of a bunch of columns in the object. Okay? So what we are doing is the following. So we get a, let me see. So yeah, so what we do is the following. So we read a Parquet file, and then we project. We only require city, state, and also zip code as the required nested data structure. So we create an alias expression. So we create alias so that when these 2 operations collab with the Parquet reader, we are able to just read 3 columns inside the nested structure. And then over here we carry the flattened structure through the repartition. So there are kind of a bunch of benefits around that. So the benefit, not only reading less data from the Parquet, but let's say you guys are using Airflow. Okay, Airflow is not a columnar data structure, it's row-wise. This still help because this help in terms of reducing the shuffle amount of data, because you are creating a subset of the view before you do shuffle. So this can help in the other situation as well, not just Parquet. Although it's gonna work better with Parquet, but it's gonna help for the data source that is not columnar format as well. So that's how we do it. And then in the final UDF, we are using the alias data instead of the original one. So that's how we implement it. And this one is already merged in the Spark 3.0. And there are some to-do we want to do on this. For example, this only support a nested column. We don't support map type yet, array type. And there is something we want to work in the future pretty soon, or we can work with community to add a support. And many different edge case, we probably also want to work on them. So it's support simple nested data structure. But if we want to get it a really full feature, we have some stuff, some work we have to work together as a community. So let's talk about some of the production query we have and see how this feature can help us. So this is from one of the jobs from the data team we have. And it's their production job. So you can see it's as Spark 2.3.1 without any feature of a nested working. So you can see the input data size. It's kind of a use case of finding the data in the, from the data lake. You just want to find couple data, and you have a filter condition on that. So you can see the input data is 7.1 terabyte, okay? And we get a really small output data, which means the whole job is kind of finding a small subset of data. And it's typical use case in the BI situation, because basically what we are doing is that you have data lake, you want to query, generating some kind of report, or you want to do some understanding, get some insight, doing some aggregation of the data. So typically, that's what's going on. So you query the big data set, and you are look at sub-condition, certain condition, And this job takes 1.2 hours to read bunch of the data over here, which is pretty slow, unfortunately. But it's good because people can wait there, play around computer, doing video game, Facebook, whatsoever. But it's not good.
How many files are there?
I think quite a lot, though. Let me see.
6,000?
Yeah, 6,000. Yeah, it's quite a lot of files. Yeah, as a Parquet file. So it's pretty big file. Okay. So with all the patch we have, and we have internal build of Spark, so we don't. Yeah. So we apply the patch with the internal build, and then you can see the input become like 840 gigabyte. And then it's reduced from 7.1 terabyte. So, a lot of reduction in terms of data reading. And it's good because you spin disk less, and save more energy. Anyway, so, and the point is that the runtime become like 3.3 minutes from like 1.2 hours.
Come on.
So, yeah. Okay. So this is good. And we find like it's 21 times faster in terms of the word clock time. It's run really fast. And we read like 8 times of the data less from the disk. And it's more like power efficient, and we use less data spinning the disk CPU time. But being said that we are all like green at Apple, we use solar panel.
Spark powered by the sun.
Yeah, powered by the sun. Anyway, so yeah. So that's the cool feature we have. Yeah, so maybe I can turn over to you to talk about some of the following work we're gonna work on.
Yeah, so there's, the work is never done when you're in big data. There's some other things that we're hitting up against that we want to work on. The one thing we didn't talk about this time, we spoke about it in Spark AI in London. We heavily use data sets. Our data scientists really like it. They're type safe. We can test them. They're very nice and very concise in the way we're doing them. The problem is the performance between data frames and data sets in Spark are huge. It's a huge penalty you pay for this. So we're actually working on doing bytecode analysis. So you can actually get almost data frame performance with data sets. And then that is my selling point, because there's a presentation about this tomorrow from Anton and DB. So please don't miss it. And spoiler alert, this PR is coming out tomorrow. So you guys can look at our proposal on how this is going to work. So yeah, just at Apple, we're kind of scratching our own itch, and luckily the work we're doing is also helping other people. Those of you that were really shy about the performance at the beginning of the presentation, Spark 2.4.1 should have some of these patches, and then 3 will have the rest coming out later in the year. And then because we know that everybody likes taking pictures of the JIRAs, we made one slide, so you don't have to take pictures all over the place. If you want to go check them out, they're right here. And if you're interested in any of this work, Apple has a booth downstairs. We're hiring for a whole bunch of positions, machine learning, data science. If you want to become a committer, work in open source, come talk to us, grill us about whatever you want. Sadly, I don't have iPhones to throw away. I guess it's just koalas in the morning. But yeah, thank you for your time, and let us know if there's any questions. If you have questions, please go to the microphones.
Sure. So I have a question about the implementation of nested column flattening. I wonder, how does that flattening happen? Does Spark still have to load the original data in memory and flatten that within memory and cache that data, or the flattening directly happen on disk?
Oh yeah, good question. So, so basically, it's a view of the data when we create an execution plan. So the flattening is actually done like it's kind of virtually flattening. So basically, that's how we So let me see how to explain it easily. So basically, in the execution plan, finally we would have we get the data, so we get subset of the data, right? We are actually projecting the subset of the data by applying the smaller set of schema. And then we're gonna do the whole stage cogent inside Spark. You probably hear that for from other speaker or whatever, or from other source. So basically over layer, you're gonna generate a code. The genetic code will like, create a alias, for example, like, a temporary variable that will hold in the data structure, the data. So it's actually done in memory, not in the disk. And it's really efficient, so it's just do it once and read it in the memory. Yeah, and then later on, the actual like code will reference the alias variable instead of like using the real like the one from like disk or whatever. Yeah.
Can you use the microphone so they can hear from the other
Yeah.
side, please?
So the nested data has to be loaded into memory once.
Yeah.
And
Of
then
course, you
flatten.
need to read the data
UVM, right.
whatsoever, right? You read it into disk, from disk to memory as the flattened data structure,
Yeah.
and then we create an attribute, alias attribute on top of the, the flattened data structure.
Okay.
Yeah, and then later on we can use it. So it's create a bunch of code,
I
like
see.
the whole stage code.
So this will go to the implementation of the as keyword.
Yeah, exactly.
during the
It's gonna go
query.
through the implementation of the ASCII.
Oh.
Yeah,
Thank you.
you bet.
Is there a question on this side?
I think like question was along the same line, and also I think so when you read the data from Parquet, you can pass a schema, right?
Yeah.
So if I want to pass a schema, then probably I should use a filter later after passing the schema, reading the data.
Oh, can you
Is
say
that-
it again?
So like when you read the data from a Parquet format and
Yeah.
you pass a schema, which probably I have already shortened the columns, right? And
So
then
yeah, you
like,
can apply the schema on the Parquet file.
right.
Yeah.
And then like if I also want to use the filter function, then should I use the filter later?
Oh, that doesn't matter. So the catalyst optimizer should figure out for you.
Okay. So you
Yeah.
think the performance will be the same?
Yeah, should be similar. Yeah, should be the same. Yeah.
Okay.
That seems like a coding style.
Yeah, it's kind of, yeah.
Yeah, filter early, filter often.
Yeah, but in theory, okay, how it work will be like, let's say you read the data as data frame, you get whatsoever, and then you can apply a bunch of transformation after the data frame. So if you don't mutate certain column, for example, then the filter can be pushed down earlier
Okay.
inside Spark. So Spark just look at, whether you mutate something. If not, you can push down all the way from the top into the bottom. So that should be, be automatically figured out by Spark. Yeah, in general. There are some edge cases that doesn't work properly, but there is the general theme. Yeah,
Okay, cool.
Yeah.
Thank you.
cool.
I have two questions. One is basically you mentioned this large number of fields within same column, but are those like in terms of the level of nested column? Is it just one level or there's like 10 level? Of,
It's multi-level, 5, 6 level. It's pretty deep.
okay.
Yeah.
What would be a typical like level of?
Yeah, it's like, it's pretty hard to say because, I'm not working directly with data, and then I saw data with like a 10 level, 6 level. It's
Okay.
Because, it's depending on how you model the data, because
Right.
our data engineer prefer like model the data by case class, have some kind of representation, and then they compose the case class together to into a big data structure. So that's why we have like super nested data structure. Yeah, so it's really depending on how your team work on. Yeah, but that doesn't matter because at the end
Yeah.
of the day, inside Parquet,
That makes sense.
it's actually stored in a flattened data structure.
Yeah. You also talked about like future support for map. Do you guys plan to do that in Reader or is it after Spark after the reader read everything into Spark, then you do the projection? Which way?
Oh, okay. So basically, we need a support map in order to push down to the nested. So basically, let's say you have nested column that has a map type, for example. We should be able to push down some of the predicate into the reader, and that is something we don't implement yet.
Do you need to also change the read toolpath, like Parquet Reader?
No, Parquet Reader is not required to change. It's mostly on the Spark side.
Okay.
How we call Parquet Reader. Yeah.
Thank you.
For example, like this work, we don't need to change any Parquet code base, so we need to just add those features inside Spark. So basically, inside Spark, there's an API called Data Source API, and Data Source API doesn't support this kind of feature at all right now. So we need to change the data source API such that it support like nested data pushdown, and then we need to add an implementation for Parquet so that data source API generate a plan, and then the plan can properly push it into the Parquet reader. Yeah. So there will be two work over here. Yeah.
So you mentioned at the beginning that you considered flattening the data instead of doing all this work.
Yeah.
What are the reasons that you decided to do this instead of just pre-processing and flattening it all?
Oh, okay. Good question. Yeah, so I think some people prefer to keep the data with hierarchical data structure for like an organization. So you feel like it's more organized, and also it's more tied into the data set API. Because in data set, you probably compose like, the parent object, which bunch of the case class inside that. And then if you flatten everything out, then, it's kind of like a little bit different data model. So it's hard to compose this kind of data structure using data set.
Got it.
So it's actually preference by,
There's information in the hierarchy on how these
Yeah.
come down. So by flattening out, you still have to represent those connections
Yeah.
somehow.
No, I've actually done it, so I
Oh,
know
okay.
that
There
you
you go.
have to do all that extra joins. And second thing, could you go back to the previous slide? I didn't have time to take the picture.
That guy?
Yeah, thank you.
Awesome. Any questions from this side? Cool. Well, thank you for your time, and catch us around if you see us.
cool, thank you.